Chapter: Terraform, Infrastructure as Code for the Cloud Age. Welcome to this chapter of the audiobook, where we explore a powerful tool that has become essential for modern infrastructure management, Terraform. Whether you're building on AWS, deploying a Node.js app, or managing a hybrid cloud setup, Terraform helps bring structure, reliability, and automation to your infrastructure. Terraform is an open-source infrastructure as code tool developed by HashiCorp. It lets you define your infrastructure using simple, human-readable configuration files. With Terraform, you don't click around cloud dashboards, you codify your entire setup, version it, share it, and automate deployments with ease. It's declarative, meaning you describe the end state, and Terraform figures out the steps to get there. So how does Terraform actually work? When you write a configuration, you're describing resources like EC2 instances, databases, load balancers, or even DNS settings. You run the Terraform plan command to preview changes, and then Terraform apply to execute them. Terraform interacts directly with your cloud provider's API, in our case, AWS, to provision and manage resources. It builds a dependency graph to determine the correct order for resource creation, modification, or deletion. But the real power of Terraform goes beyond provisioning. It's about why you'd choose it over traditional manual approaches or ad hoc scripts. First, Terraform can manage virtually any infrastructure, from public cloud to private cloud, SaaS platforms, and even on-premises systems. If it has an API, Terraform can likely manage it. That's true multi-cloud power. Second, Terraform tracks your infrastructure in a state file. This state file becomes the source of truth, keeping a record of what's been deployed and what its current state is. If you make changes in your configuration files, Terraform compares the desired state to the actual state and applies only what's needed to bring the two in sync. This makes changes predictable, safe, and reversible. Automation is another core reason to use Terraform. You can integrate it into C/CD pipelines, use it to manage hundreds of resources at scale, and eliminate the risk of manual error. Whether it's deploying a simple web server or a complex distributed application, Terraform brings speed and consistency to the process. Standardizing configurations is also easy with Terraform. You can reuse modules, think of them as reusable templates for infrastructure, and apply them across environments or projects. This means your development, staging, and production environments can all share the same architecture blueprint, reducing inconsistencies and improving reliability. The language used to write Terraform configurations is called HashiCorp Configuration Language, or HCL. It's designed to be readable and concise. Resources are defined using blocks that specify the provider, the type of resource, and the parameters needed. It's intuitive and easy to pick up, even for teams new to infrastructure as code. To work with Terraform, you'll primarily use the Terraform CLI, a command line tool that gives you control over planning, applying, and managing your configurations. The workflow is straightforward. Write your TF files, run Terraform init to initialize the working directory, Terraform plan to see what will change, and finally Terraform apply to provision the infrastructure. Let's bring this into a real-world context, setting up Terraform for an AWS project that runs a Node.js application. First, you'll need AWS credentials configured on your machine, either through the AWS CLI or environment variables. Then you define your provider block, telling Terraform to use AWS, along with your desired region. You can define an EC2 instance, security groups, and even user data to run Node.js as soon as the instance starts. You could also include an S3 bucket for storing logs or artifacts, and use Terraform modules to organize your configuration by environment or component. The beauty is, you don't need to manually click through the AWS console. Your infrastructure is defined, versioned, and deployable in seconds. Rollbacks are simple, collaboration is seamless, and every change is tracked in code. In short, Terraform is not just a tool, it's a mindset. It brings software engineering principles to infrastructure management, enabling teams to move fast, scale confidently, and reduce the chaos of manual configuration. Chapter: Modular Terraform Configurations and Managing Environments with Workspaces. Welcome back. In this chapter, we take Terraform to the next level by exploring two powerful features that elevate infrastructure as code from simple scripts to scalable, enterprise-grade solutions. Let's talk about modular configurations and managing environments with workspaces. As your infrastructure grows, you'll quickly realize that repeating the same code across projects or environments is neither efficient nor safe. That's where Terraform modules come into play. A module is simply a container for multiple resources that are used together. Think of it like a function in programming. It encapsulates logic, hides complexity, and can be reused anywhere. You can write your own modules or use pre-built ones from the Terraform registry. A good module is clean, organized, and flexible, with input variables and output values. For example, you could build a module for an EC2-based Node.js app. Inside that module, you might define an instance, a security group, an IAM role, and a load balancer. Then, whenever you want to deploy this Node.js app, whether to dev, staging, or production, you just call the module with a few variables, and Terraform does the rest. This approach avoids copy-pasting code. It reduces human error. And more importantly, it creates a standardized architecture across all environments. Speaking of environments, managing different stages of deployment, like development, testing, and production, is critical. Each environment usually needs its own set of resources, often with small variations. Terraform provides a feature called workspaces to help manage this cleanly. A workspace in Terraform is like a separate instance of your configuration, each with its own state file. When you create a new workspace, for example, dev, stage, or prod, Terraform keeps each environment's state isolated. That means you can use the same configuration code but apply it separately to each environment without interference. For instance, in a multi-environment setup, you might use a single Terraform module for a web app, but configure the dev workspace to use smaller EC2 instances, fewer replicas, or even dummy database credentials. The prod workspace would use high-performance instances, stronger security settings, and fully managed databases. To switch between workspaces, you simply use the command terraform workspace select. You can also create a new one with terraform workspace new. Behind the scenes, each workspace maintains its own state, which lets you test changes safely in dev before applying them to production. Modules and workspaces together bring structure and discipline to your infrastructure code. They let you reuse configurations, separate concerns, and scale operations across multiple teams and environments. Instead of maintaining separate configuration files for each environment, you manage everything through variables and workspaces. Your modules become building blocks, and your environments become isolated, repeatable layers of infrastructure. This combination of modular design and environment control is what makes Terraform such a game changer for DevOps and cloud engineering. You're not just automating tasks, you're building a scalable, maintainable, and highly reliable infrastructure system. Chapter: Understanding Terraform State. Welcome back. In this chapter, we're diving deeper into one of the most critical pieces of Terraform's architecture, Terraform State. Whenever you apply a Terraform configuration, it doesn't just go out and build infrastructure. It also keeps track of what it built. This record, this memory, is stored in what's called the Terraform state file. Understanding and managing this file is essential for working effectively with Terraform. So what exactly is the state? Terraform state is a snapshot of your infrastructure as Terraform knows it. It includes every resource you've created, their properties, metadata, and even dependencies. When you change your configuration, Terraform doesn't blindly rebuild everything. Instead, it compares your updated configuration to the current state and calculates exactly what needs to change. This is what makes Terraform smart, safe, and efficient. By default, Terraform stores the state locally in a file named terraform.tfstate. It lives in the working directory where you run your commands. That might work fine for a solo project or for testing, but in real-world scenarios, especially when working in teams, you need more. This brings us to remote state storage. Remote backends let you store the state file in a centralized location, like Amazon S3, Google Cloud Storage, Azure Blob Storage, or even Terraform Cloud. This is crucial for collaboration, because it ensures that everyone is working off the same version of the truth. It also avoids the danger of someone accidentally applying outdated changes based on stale local state. Let's say you're working on a team, and one engineer updates the infrastructure by adding a new load balancer. The state reflects that. If you're still using a local state file, your configuration may not be aware of that update. But with remote state, Terraform checks the latest version stored in the cloud before planning any changes. Another benefit of remote state is that it supports locking. When one person is running Terraform apply, the backend can lock the state file to prevent others from making changes at the same time. This prevents race conditions and helps keep your infrastructure consistent. Now, how do you set it up? For example, in AWS, you might configure your backend to store state in an S3 bucket. With locking provided by DynamoDB, you declare this configuration in your Terraform files using a backend block. Once it's set up, Terraform handles state storage and locking automatically, so you and your team can focus on writing infrastructure, not worrying about conflicts or version mismatches. You might be wondering, what's inside the state file? It's a JSON document. You can even open it and read it. It includes every resource and its attributes. However, manually editing this file is strongly discouraged. A corrupted or incorrectly edited state file can wreak havoc on your infrastructure. Terraform provides commands like terraform statelist to see what's in the state, and terraform state show to inspect a specific resource. If needed, you can even move resources between modules or rename them using terraform state mv, or remove something completely with terraform state rm. As powerful as Terraform is, it depends entirely on the integrity of the state file. That's why it's good practice to regularly back up your state, keep it secure, especially if it contains sensitive data, and use remote backends for any serious project. State is the heart of Terraform's ability to know what to do, and just as importantly, what not to do. Chapter: Writing Reusable Terraform Modules. Welcome back. In this chapter, we're stepping into one of the most powerful and elegant features in Terraform: reusable modules. Modules turn your infrastructure into building blocks, helping you write clean, organized, and scalable code. So what exactly is a Terraform module? At its core, a module is just a collection of Terraform configuration files grouped together in a directory. You can think of it like a function in a programming language. Instead of repeating code, you write it once inside a module and call it whenever and wherever you need it, just by passing in variables. Let's say you need to create a VPC with subnets, routing tables, and security groups. You could define it all in your main Terraform file, but that gets messy fast, especially if you're creating similar environments for dev, staging, and production. With modules, you can extract that logic into a dedicated folder. Then, from your main configuration, you call that module with a few lines, passing in variables like CIDR blocks, region, or environment name. The module itself typically includes 3 files. Main.tf holds the core resources, variables.tf defines what inputs the module expects, and outputs.tf returns values that other parts of your code can use. This clean separation makes modules easy to understand, easy to test, and easy to reuse. Now let's walk through an example. Imagine you're building a reusable module to deploy a Node.js app on AWS EC2. Your main.tf file might define the instance, security group, and user data for the startup script. The variables.tf file lets users customize the instance type, the key name, and the AMI. And your outputs.tf could expose the public IP address and instance ID. When using this module in a real project, you just call it using the module block. You specify the source path, either a local folder, a Git repo, or a Terraform registry module, and pass in the inputs like so: instance_type equals t3.micro or environment equals staging. You can even nest modules. For example, your application module could call a networking module, which itself uses a security module. This lets you break down your infrastructure into logical layers: compute, networking, storage, and more. A big benefit of reusable modules is consistency. You avoid duplicated logic. You enforce naming standards and security best practices. You make your infrastructure predictable and scalable. And when you need to make a change, you do it in one place. But it doesn't stop there. Modules support versioning, so you can publish them and update them just like software packages. You can create a module registry for your team or organization, where everyone pulls from approved, battle-tested infrastructure code. Imagine being able to spin up a production-ready Kubernetes cluster or a secure S3 bucket setup with just a few lines of code. That's the power of modularity. To make your modules even more flexible, you can provide default values for variables, validate inputs, and document them using the description attribute. This makes modules easier to use, even for newcomers. One best practice: keep modules focused. A good module does one thing well: avoid mixing unrelated resources into the same module. This keeps things easy to debug and maintain. In summary, reusable modules turn your Terraform setup from a one-off script into a scalable infrastructure platform. They make your code cleaner, your deployments faster, and your architecture more reliable. Chapter: Variable Management and Secrets Handling. Welcome back. In this chapter, we're going to explore one of the most practical and sensitive parts of working with Terraform: managing variables and handling secrets. When writing infrastructure as code, hard-coding values into your configurations can quickly lead to trouble. It's inflexible, messy, and risky, especially when those values include sensitive data like access keys, passwords, or private IPs. Terraform provides a robust system for defining and managing variables so you can write reusable, dynamic, and secure infrastructure code. Let's start with input variables. Input variables let you parameterize your Terraform configurations. Instead of hard-coding a region or an instance type, you declare a variable, and then pass in the value at runtime. This makes your code flexible and reusable. You define variables in a variables.tf file using the variable block, where you can also include default values, descriptions, and type constraints. When it comes time to supply these values, you have several options. You can pass them directly via the command line with var, store them in a terraform.tfvars file, or load them from environment variables using the tf_var_ prefix. Terraform will automatically pick up and merge these values. Now, onto a more sensitive topic, secrets. It's incredibly important that secrets, like database credentials or API tokens, are never stored in plain text inside your Terraform files. Terraform doesn't encrypt variable values by default, so you need to be intentional about how you manage them. One common practice is to load secrets from environment variables. For example, setting tf_var_db_password in your shell ensures Terraform picks it up without needing to store it in your code. You can also use a fvars file, but be sure to add that file to gitignore so you never accidentally commit sensitive data to version control. Another more secure approach is integrating secrets management tools into your Terraform workflow. Tools like HashiCorp Vault, AWS Secrets Manager, and Azure Key Vault allow you to store and retrieve secrets dynamically at runtime. With these integrations, you can pull in secrets using data sources or environment variables without ever writing them into your code. Terraform also supports sensitive output values. If you declare an output as sensitive equals true, Terraform will mask its value when displaying it in the CLI. This is useful for returning secrets that need to be passed to another system, but shouldn't be visible to the user. As a best practice, treat secrets with the same care you would give to encryption keys or passwords. Never log them, never commit them, and always review your Terraform state files, because if you're not careful, secrets can end up there too. Speaking of which, the state file can be a blind spot for secrets. If your resources include secrets, say, a password for a database, Terraform might store it in plain text inside the state file. That's why it's critical to store your state in a secure remote backend, like an encrypted S3 bucket with restricted IAM access. You might even consider enabling server-side encryption and versioning. In summary, Terraform gives you powerful tools for managing variables, but it's your responsibility to handle secrets securely. Use environment variables, ignore local secret files, leverage dedicated secret managers, and never take state file security for granted. With strong variable management and secret handling in place, your infrastructure becomes not only scalable and dynamic, but also safe and production-ready. Chapter: Terraform Provisioning. Welcome back. In this chapter, we're diving into the heart of what makes Terraform more than just a tool that draws diagrams. This is where it brings your cloud infrastructure to life, through provisioning. Provisioning in Terraform refers to the process of creating, configuring, and initializing your infrastructure resources using the defined configurations. Once your code is written and your variables are set, provisioning is what actually builds your infrastructure in the real world. Terraform uses providers to interact with cloud platforms and other APIs. These providers act as a bridge between your code and your infrastructure. For example, the AWS provider communicates with the AWS API to create EC2 instances, S3 buckets, Lambda functions, and more. There are providers for all the major platforms: Google Cloud, Azure, Kubernetes, GitHub, Datadog, you name it. If there's an API, there's probably a Terraform provider for it. To use a provider, you simply declare it in your configuration using the provider block. You can specify region, credentials, and other authentication details. When you run Terraform in it, Terraform downloads the required provider plugins and prepares them for use. Now let's talk about resources, the actual infrastructure components you want to provision. These are defined using the resource block. Each resource maps to a specific type of object in the provider, like an AWS_instance or a Google_compute_network. Once defined, Terraform handles the lifecycle: create, read, update, and delete. When you run Terraform apply, it compares the current state to the desired configuration, figures out what needs to change, and executes the necessary API calls to make it happen. This is the core of Terraform's declarative approach. You tell it what you want, and it figures out how to get there. Now, sometimes creating a resource isn't enough. You also need to run custom scripts after the resource is provisioned, maybe to install software on a virtual machine or configure the environment. That's where provisioners come in. Provisioners are used to execute scripts or commands on a resource after it's been created. The most common types are remote exec and local exec. Remote exec connects to your resource, like an EC2 instance, over SSH and runs commands on it. Local exec runs commands on your local machine, which can be useful for notifications, scripting, or integrations. But a quick note of caution: Terraform's core philosophy is declarative, and provisioners introduce imperative logic, so they should be used sparingly and only when there's no better alternative. If you're doing heavy post-provisioning work, consider using configuration management tools like Ansible, Chef, or Cloud Init scripts instead. Another key feature in provisioning is the use of data sources. These let you query existing infrastructure that wasn't created by Terraform. For example, You might use a data source to fetch an AMI ID for a specific Linux distribution in AWS, or look up a VPC that was created outside your current configuration. Data sources make your configuration smarter and more dynamic, letting Terraform adapt to your existing environment. All of this comes together in a seamless flow. Terraform pulls in data, configures providers, defines resources, and optionally runs post-deployment steps. It automates infrastructure from start to finish, turning what used to take hours or days into a repeatable, reliable process you can execute in minutes. And because Terraform tracks state, it knows exactly what's already been provisioned. If you change something in your configuration, like updating an instance type or modifying a security group, Terraform only touches what's needed. This incremental and intelligent approach to provisioning is what sets it apart from traditional scripts or cloud consoles. Chapter 4_each, count, and dynamic blocks. Welcome back. In this chapter, we're exploring the tools Terraform gives you to scale and simplify your infrastructure code, without duplicating lines or repeating yourself. We're talking about _each, count, and dynamic blocks. Let's start with count. Count is the most basic form of resource replication. When you need to create multiple instances of the same resource, you can add a count argument, followed by the number of times you want Terraform to create it. For example, you can spin up 3 EC2 instances using a single resource block by simply writing count equals 3. Terraform will generate resources with indexes 0, 1, and 2 that you can reference inside the resource. But what if you want to create multiple resources based on a list of specific values? That's where _each shines. _each allows you to loop over a map or set of strings, and it gives each instance a unique key. So instead of having indexed resources like with count, you get named instances. Imagine creating security groups for different services. You could use _each with a map of service names to port numbers, and Terraform will create one security group per entry, each named and customized according to the map. _each is especially useful when dealing with resources that have unique identifiers or when you need to access instances by name rather than number. It adds more clarity and control to your infrastructure logic. Now, let's talk about something even more dynamic: the dynamic block. Terraform configurations often include nested blocks, like ingress and egress rules in security groups. But what if the number or content of those nested blocks depends on a variable or list? Instead of repeating the same nested block multiple times, you can use a dynamic block to generate them programmatically. A dynamic block lets you loop over a list or map and inject nested blocks into a resource definition. You specify what kind of block to generate, like ingress, and then provide content for each iteration. This makes your code cleaner, more flexible, and easier to update. It's especially helpful when you're dealing with variable length configurations or optional structures that don't always exist. To give you an example, suppose you have a list of ports for a security group. You can use a dynamic ingress block to create one rule per port, all from a variable, rather than copying and pasting the same structure over and over. Now here's a practical takeaway. Count is great for simple replication. _each gives you more descriptive control when you're looping through named items. And dynamic blocks unlock flexibility in places where nested structures need to adapt to different inputs. Used together, these tools help you write Terraform that is modular, dry, and highly maintainable, no matter how complex your infrastructure becomes. Terraform supports testing and validation with Terraform Validate, Teflint, and Pre-Commit.